Next up, let's view a couple more examples of the alternating series test. So first up, we're going to determine if the series converges or diverges, and our series is the sum from n equals 1 to infinity of negative 1 raised to the n power times the square root of n over 2n plus 3. Now, first thing that we're going to notice is because there's an alternator in here, I want to make sure that I'm using the alternating series test for it. So first step to any of these is going to be identify what tests that you want to use. In this case, because it has an alternator, that's why we want to use an alternating series test. Now we're going to consider the sequence that we would get by removing the alternator. There are two things to show for this sequence. So first thing I want to do is show that the sequence is decreasing. Now technically we also have to show that the sequence is positive, but with n equals 1 and getting bigger, if we input a positive value in here, everything is still going to be positive, so that part is less important. Now there are two ways to show that the sequence is decreasing. We can either show that b sub n plus 1 is less than b sub n, or we can talk about the generating function for this and prove that the first derivative is always going to be negative for x being greater than 0. Let's set up both just so that we can make a decision about which one we want to do. So in this case, we would be trying to show that the square root of n plus 1 divided by 2 times n plus 1 plus 3 is less than the square root of n over 2n plus 3. For this one, we would be taking a derivative and trying to show that it's negative. So using the quotient rule, this would be low d high less high d low over the square of what's below. Now again, you're allowed to do either one of these. I think I'm going to stick with the one on the right. The derivative doesn't look like it's going to be too bad. So first off, distributing the 1/2 x to the negative 1/2 power, we will get, let's see, 2 and the 1/2 will cancel out. X times x to the negative 1/2 power will be x to the 1/2 power, plus 3/2 x to the negative 1/2 power, minus 2x to the 1/2 power, all over 2x plus 3 quantity squared. To clear out the fractions that we have in the numerator, I'm going to multiply top and bottom by 2 square roots of x. And maybe that numerator will be a little bit nicer to work with. So 2 square roots of x times the square root of x will be 2x plus, that'll wind up being 3, and then this will wind up being minus 4x all over 2x plus 3 quantity squared times 2 square roots of x. Now that numerator is going to wind up being 3 minus 2x. Now I can verify that the denominator, we're only going to be plugging in positive values for x anyway. So with that in mind, as long as the numerator is less than 0, we're going to be okay. And I notice that if we were to plug in x equals 1, we would get a positive value up here, but as soon as I plug in x equals 2 or bigger than 2, what we can prove is that f of x is going to be f prime of x is going to be less than 0 for all x greater than 3/2. So what we showed is that this thing is not always decreasing, but rather we showed that it's going to be decreasing eventually. Decreasing eventually means it doesn't necessarily start decreasing, but eventually it does become decreasing. So I guess if push came to shove, what we could do is just plug in n equals 1, get a separate term, and then have the sum from n equals 2 to infinity, and then the decreasing condition would be satisfied. So that's taken care of. The second part usually goes a little bit quicker. We can probably fit it right here. Next we need to show that the sequence converges to 0. Now technically in its current form it would be infinity over infinity. Can't really plug in infinity, but we'll pretend like we can. So we'll apply L'Hopital's rule once and differentiate the top and bottom with respect to n. Your numerator is going to be 1/2 times n to the negative 1/2 power. Your denominator is going to be 2. Now with that in mind, doing a little bit of algebra here, this is going to be 1 over 4 square roots of n. If we let n go to infinity, this is going to go to 0. So over here, I got my well done steak. Over here, I got my ketchup. Therefore, by the alternating series test, the original series, the original alternating series, sum from n equals 1 to infinity of negative 1 to the n power times the square root of n over 2n plus 3 converges. As soon as we show the sequence is decreasing and the sequence converges to 0, the alternating series test says we good. For another example, let's try this one. Determine if the series converges or diverges. This time we have the sum from n equals 1 to infinity of negative 1 to the nth power times n squared over n squared plus n plus 1. Now, as I mentioned before, first thing on these problems is determine what series test we want to use. Because it has an alternator, we're going to use the alternating series test. And the corresponding sequence that we're talking about is n squared over n squared plus n plus 1. We want to show two things for this series. Now in the last one we showed that it was decreasing, then we showed that it converged to 0. You're allowed to go in either order though. So what I'm going to do is try to show that this thing goes to 0 first. Now technically if we were to try direct substitution property on this, your numerator is infinity and your denominator is infinity. There are a couple different things that you can do. You could apply L'Hopital's rule, but I'm going to go with an algebraic trick from back in Calc 1 and divide top and bottom by n squared. This is going to leave me with the limit as n goes to infinity of, your numerator is now 1, your denominator is 1 plus 1 over n plus 1 over n squared. If we allow n to go to infinity, this converges to 1. According to the alternating series test, this was supposed to converge to 0 in order for the series to converge. Well, if it doesn't converge to 0, then you are allowed to draw a conclusion. Therefore, by the alternating series test, or technically the divergence test from back in section 11.2, the alternating series, sum from n equals 1 to infinity of negative 1 to the nth power times n squared over n squared plus n plus 1 diverges. So what I was just told is we don't serve ketchup at this restaurant, to which I say good day. I say good day. I will not give you my business. The alternating series diverges.